Good afternoon, ladies and gentlemen. My name is Gautam Kalghatgi, and I would first of all like to thank the organizers for giving me a chance to give this talk. And as you can see, the title of the talk is Should We Continue Doing Engine Research? And the papers that I've listed on this page at the bottom contain more detail about this, and you're welcome to go and look at them at your leisure. Now, why do I raise this question? This is because, as all of you know, there is widespread belief that the future of transportation is electric, and the internal combustion engine, which actually currently powers about 99.9% of transport, is going to be dead very soon. If that is indeed the case, there won't be any need to do engine research in the future, and conferences like this will be largely redundant. However, as we will see, the scale of the transformation required is extremely large, and there are very large economic and environmental barriers for this transformation to take place. And therefore, internal combustion engines will continue to power transport largely for decades to come. And these need to be improved continuously. And therefore, there'll be a lot of scope for engine research in the future as well. Now, let us look at some of the details. Now, globally, transport accounts for about 14% of greenhouse gas emissions. That includes CO2, methane, and nitrous oxide and other greenhouse gas emissions. About 20% of total energy use and 23% of CO2 emissions. In 2019, across the world, there were over 1.2 billion light-duty vehicles and over 350 million commercial vehicles. In the UK, for example, there are 37 million light-duty vehicles. And I think in China, there are about 250 million cars. I suppose people in the audience might have better figures than this, and they can look it up. Now, light-duty vehicles account for 44% of global transport energy demand. Transport, of course, is essentially driven by liquid fuels. This is because liquid fuels have high energy density, they're easy to store and transport, and they have become the fuels of choice for transport. And therefore, a very extensive infrastructure worth trillions of dollars, maybe $80 trillion, has grown over the past century or so, and it's very difficult to replace this. The demand for transport fuels is extremely large. It's about 4.9 billion liters each of gasoline and diesel and 1.2 billion liters of jet fuel every day. So we are talking about roughly 11 plus billion liters of liquid fuels each day, which accounts for about 105 terawatt hours of fuel energy. Petroleum, that's oil, and transport are very closely linked. 95% of transport energy comes from petroleum-based fuels, and 60% of oil goes to make transport fuels. And also, the demand for transport energy is growing at an average annual rate of about 1%. You have to take out 2020 out of this equation because of COVID and so on, but that's the general trend. And all this growth is occurring in non-OECD, that's developing countries. So the demand growth for transport energy is greater in the commercial transport sector compared to the light-duty vehicle sector, because light-duty vehicles essentially run on spark ignition engines, so that's gasoline engines, about 85% of them across the world. And there's, of course, greater scope for efficiency improvements in spark ignition engines. For example, they can use hybridization, even electrification, which we'll come to in a minute. And also, on average, the future average car will not be in places like the United States, where the very big cars, which are very inefficient in terms of fuel use. They'll be in countries perhaps in Asia, so they'll be lighter, smaller, cover less distance. So the result of all this is going to be that there will be a greater increase in demand for diesel and jet fuel than in gasoline. So the oil refineries will have to process more oil in order to produce more diesel and jet, but they will be left over with material used for gasoline manufacture, which is basically low octane gasoline components. So there is likely to be much greater availability of low octane gasoline components in the future. And we'll come to that. This is fairly important. Anyway, I'll restate another important point that if you look at most credible projections, even by 2040, transport will be dominated by combustion engines. 85 to 90% of transport energy will still come from oil running these internal combustion engines. So it's absolutely essential to improve such engines to improve the sustainability of transport. Now let's look a bit more detail in the electrification of transport, which is such a hot topic. As you know, there are different degrees of electrification. Only the battery electric vehicles, BEVs, do not have an internal combustion engine, and all their energy comes from the electricity grid. And therefore they need a fairly large battery to allow sufficient range on the battery alone. Then there are the hybrid electric vehicles, HEVs, such as the Toyota Prius, which have much smaller battery. However, all their power comes from the internal combustion engine. But the battery and the motor and the electric transmission system allows this internal combustion engines to be much more efficient by managing the energy flow through the system. And also it allows the recovery of brake energy. In between the two are the plug-in hybrid electric vehicles, which have batteries which are in between in terms of size of the two technologies, but they also have an internal combustion engine. So if the battery actually runs out of charge, the internal combustion engine will take over, and the range for PHEVs on which they can just run on electric power is quite small compared to the battery electric vehicle. PHEVs are obviously more expensive than BEVs because they need to have two full power systems. HEVs are the most practical and proven technology, and they have been available for some time, and they reduce the fuel consumption of gasoline light-duty vehicles by up to 20%, depending on how they are driven. If we now look at the actual scale of the problems. For example, if you look at the BEV numbers, they are increasing extremely rapidly because the sales of battery electric vehicles is increasing rapidly. On the left-hand side is the sales figures for China. And if you look at the whole world in 2019, about 2.1 million battery electric vehicles were sold. That's about 2.3% of all sales of all LDVs. Incidentally, we are focusing on battery electric vehicles because if you want to eliminate ICEs, basically you have to change all light-duty vehicles to battery electric vehicles. So by the end of 2019, the BEV stock in the world was about 2.6 million in China. About 1% of passenger cars. And if you look at the whole globe, the global stock of BEVs was about 4.8 million in 2019. And they were mostly small cars, and that accounts for about 0.4% of total number of light-duty vehicles. In 2040, of course, global LDV numbers are expected to be between 1.7 and 1.9 billion. So it will be, so you want to replace current numbers of LDVs, you need to increase the number of BEVs by a factor of 300. And if you look forward to 2040, it has to be anything between 300 and 500 times more battery electric vehicles compared to now. So if ICVs are to be eliminated from LDVs of all sizes by 2040, battery capacity needs to increase by a much larger factor, perhaps by well over 500, because they need much larger batteries, the bigger cars and with bigger ranges. But even then, it still addresses only 45% of transport energy demand. Such a massive increase in BEVs will have very significant and perhaps unsustainable environmental and economic impacts. So what are these environmental impacts of BEVs? Clearly, the greenhouse gas impact depends on how electricity used to power BEVs is generated. If coal is used to make electricity, the CO2 emissions from power generation will be very high, and the GHG impact of BEVs also will be very high. Battery production itself uses a lot of energy, much more than for making internal combustion engines. And it could generate up to 200 kilograms of CO2 per kilowatt hour of battery capacity. Of course, if fossil-free energy used for manufacture of BEVs, batteries, this will be much less. In many parts of the world, certainly in India and China, coal is a very big factor in power generation. And in these countries, BEVs could cause more CO2 than equivalent internal combustion engines. Then there are other pollutants like sulfur dioxide, NOx, and particulates if coal is used for manufacturing, making electricity. Of course, this will not happen at the point of use of BEVs, but will be exported to where the power is generated. Nevertheless, it's an important source of pollution. There are also very serious health problems associated with mining for materials for batteries, particularly for cobalt. And this is measured by the human toxicity potential, HTP. HTP is expected, or actually calculated to be about 3 to 5 times worse for BEVs than for ICEs, where the HTP comes about from exhaust pollution. Also, mining for materials like lithium uses a lot of water, and there are water and water toxicity impacts associated with mining. All these problems, many of these problems anyway, are not actually discussed very much at the moment. They are swept under the carpet. This is because the number of BEVs is relatively small, and also it occurs in faraway places where the BEVs are not being used. However, if we are talking about an increase in BEV numbers by a factor of 300 to 500, these problems cannot be ignored. They will come to the fore. And the environmental movement will be very, very concerned about this. Also, the amount of earth needed to be moved to get to materials needed is on average about 500 times the weight of battery. This is to do with mining again. For example, a 100 kilowatt hour battery might require about 270 tons of rock moved to get to the materials needed. And they, as I've already said, they use a lot of water. In general, the larger the battery, the worse these impacts. So BEVs are not green or clean. In fact, I think they should be called EEVs, emissions elsewhere vehicles, because they export the pollution mostly to away from where the BEV is used. Now, full electrification is not really relevant to most commercial transport that is outside the light-duty vehicle sector. For instance, a 40 US ton lorry with a range of 800 kilometers will require a battery of at least 1,000 kilowatt hour capacity, which will weigh at least 6 tons in weight and will cost over 180,000 US dollars. And the charging time would be around 14 hours on a Tesla supercharger at 0.125 megawatts. Now, if you look at the aircraft, there's a lot of fantasy about running air travel by batteries. But let's consider this A320, which is a medium size, medium range jet, it carries 266 megawatt hours of fuel energy. A battery pack carrying the same energy would weigh 1,640 tons, or 19 times the maximum takeoff weight of the aircraft. And at 1 megawatts charging, I mean, remember the Tesla supercharger is 0.125 megawatts, it would require 11 days to charge. This is also true about big ships carrying a lot of cargo across the oceans. For example, the container ship Benjamin Franklin carries 4.5 million gallons of fuel, or 170 million kilowatt hours of fuel energy. And the battery pack to carry this much energy would weigh 5.8 times the dead weight tonnage of the ship. So this is essentially battery electric vehicles are confined to the light duty vehicle sector. There's quite a lot of talk that, of course, batteries will improve, and quite often Moore's law is cited. Moore's law is used to demonstrate how in the microprocessor industry, weight and cost have come down so dramatically. However, this is really not applicable to batteries. In fact, Václav Smil, who knows a lot about these things, calls it Moore's curse. In batteries, ions are the workhorses, and they occupy space, unlike in microprocessors or in your phone, etc., where electrons do the work and they don't occupy space. And that's why, in order to significantly improve battery in terms of weight and so on, the battery chemistry will need to be completely different. Even then, we should not expect gains in performance and reduction in cost at greater than about 3% per year, generally, from now on. I mean, because this is what happens in the outside the microchip world, as Smil has pointed out. And also, there is a myth that autonomous cars will accelerate the spread of BEVs. I don't think this is quite true, because level 5 autonomy requires extra power between 1.5 and 3.75 kilowatts because of additional computing and the sensors. In addition, you have to think about 1 to 5 kilowatt hours for heating and cooling. So we are talking of minimum of 2.5 kilowatts hours, even if the car is sitting around like a New York taxi waiting for customers. So over 24 hours, that amounts to about 60 kilowatt hours. So if a car has a 50 kilowatt hour battery, it cannot go very far on this. Therefore, the best solution for an autonomous car is actually an HEV, which does not have this problem because it carries enough fuel and an engine. There are economic and other implications of forced electrification of light-duty vehicles. Charging infrastructure, for instance. In the UK, 45% of the cars have to park on the streets, and they need public charging points to encourage people like that to buy battery electric vehicles. And I'm sure this is the case in China too. So in the UK, it's expected that such infrastructure will cost between 30 to 80 billion pounds. There's also the lost government revenue from fuel tax, because many countries raise a lot of money by taxing the sale of fuels. In the UK, it's about 35 billion pounds a year, and this at some stage will have to be recouped if the sales of petrol and diesel and the aviation fuel go down. Then there is the continuing incentives to persuade motorists to buy BEVs, because the upfront cost might not come down very much compared to the ICE vehicles by 2030. There is a recent SAE paper which goes into this. For instance, in the UK, the Nissan Leaf costs £29,000, which is the battery electric vehicle, which is twice as much as the Nissan Micra, which is a comparable size internal combustion engine vehicle car, which costs only about £14,000. So then there is the cost and availability of extra electricity that is needed. Then the electricity distribution network, particularly at the micro level, will need to be redesigned at great cost. This paper that I've referred to here is really worth reading at the details of such changes that are required. Also, there is a problems and costs of recycling the batteries, because batteries are very heavy and they are very complicated, and it will take a lot of development to make the recycling profitable or worthwhile in the future. But it might happen, but it will take some time. There's also the availability of critical materials like cobalt and lithium and so on to replace all the light-duty vehicles. Because remember, we are talking about on a global level, or even in a national level, like for the UK, an increase in the number of battery electric vehicles by a factor of 300 to 500. So this is going to have a huge impact on this material availability. There are also ethical issues associated with the mining of metals. Because, for example, in the Congo, where in cobalt mines, a lot of young children work in extremely unhealthy circumstances, which has attracted a lot of attention already. Well, even if you look at alternatives to petroleum-based fuels, like conventional fuels like diesel and gasoline, what you find is they also start from very low base, and there are significant barriers to unlimited growth. What are these fuels? For example, we already have biofuels and natural gas, liquid petroleum gas, dimethyl ether, methanol, hydrogen. They're already there or are being researched very intensively. But they're not expected to take much more than 10 to 20% of the share of transport energy by 2040, because they start from a low base and they have significant barriers to unlimited growth. Remember, right now they take about 5% share of the transport energy. So we are talking about doubling their share, but still they cannot replace gasoline and diesel and aviation fuel in the short to medium term. So even in 2040, most credible projections show that 90% of transport energy will still come from petroleum-based fuels powering internal combustion engines. And the improvement of such systems is absolutely essential to ensure the sustainability of transport. So how do we go forward to ensure the sustainability of transport? And this is my view on this. I think there are three stages. In the first stage, conventional engines that we know using known fuels such as gasoline, diesel, compressed natural gas, liquid petroleum gas, biofuel, and so on, improve and then reduce the greenhouse gas and other pollutants. So how do we do this? Through better combustion, better control, better after-treatment systems, coupled with partial electrification, such as in hybrid electric vehicles. It might also require some changes in fuels. For example, gasoline anti-knock quality might need to be increased to enable higher efficiency spark ignition engines. In the second stage, we can think of developing new fuel engine systems to allow greater scope for improvement. We could also think of unconventional engines like opposed piston two-stroke engines, and using new fuels. New fuels meaning not really limited by existing specification, not like the fuels that we are selling in the market, but this will also offer further flexibility. And such approaches will also help mitigate future supply demand issues. For example, as I said right at the outset, we can expect more availability of low octane gasoline. And if we can develop better engines using such fuels, there will be a lot of win-win solutions. Then in the final stage, as in the longer term, as overall energy system decarbonizes and battery technology develops, there'll be increasing role for battery electric vehicles and hydrogen and other things like this. But we must emphasize that changes like this need to be assessed on a cradle to grave or a life cycle analysis basis, though some changes may be forced. What is the scope for improving internal combustion engines? There is a recent paper that we published, Leach et al., which you can look up, which addresses this issue. Actually, there's a significant scope for improving efficiency of spark ignition engine through lean burn, downsizing and turbocharging, compression ignition, using better control, and so on. For example, in the US already, the best-in-class efficiency is about 16% better than the average for cars of similar size and performance in the market. Gasoline direct compression ignition engine developed by Delphi shows a 25% improvement. Compared to 2015 fleet averages, a 30% improvement in the US market is easily possible with combustion system improvements alone. This can be further improved and fuel consumption can be reduced by up to 50% by using lightweight materials, vehicle downsizing and partial electrification, demand reduction, and improved after treatment systems with particulate filters, you can get zero particles, and with modern catalysts and intelligent controls, you can actually get the exhaust to be much cleaner than the intake in many parts of the world. So there's a lot of scope for improving both the efficiency and the cleanliness of internal combustion engines. There is also additional scope for with so-called low carbon fuels. I won't go into this, but only if they make sense. That means they have to be assessed on a proper life cycle basis. Let me give some examples of fuel engine system development. Gasoline compression ignition, GCI, is something that's very close to my heart. It's essentially to run CI engines on low-octane gasoline rather than diesel fuel. The diesel combustion system is the most efficient internal combustion engine system. However, for historical reasons, it's been using diesel fuel, which ignites very quickly on injection into the cylinder before it has a chance to mix with oxygen in the cylinder sufficiently. And this leads to significant amounts of particulates and NOx. However, if you inject gasoline type fuel into the diesel engine, the fuel has ignition delay and it won't ignite straight away, and it will have much more time to mix with oxygen in the cylinder, and you can very significantly reduce the formation of NOx and particulates. To cut a long story short, the overall greenhouse gas and efficiency benefits could be as high as 25 to 30% with respect to spark ignition and about 5% with respect to diesel engines. The engine itself will be simpler and cheaper because you require low injection pressures. You don't rely on high injection pressures to promote mixing of fuel and air, oxygen in the cylinder. And the after treatment focus will be on hydrocarbons and CO control rather than NOx and soot. I won't go into all these details, but you can read up on this. And the fuel itself can be very low octane gasoline. It need not be the gasoline that you buy in the market. So there is no stringent requirement also on volatility, so that the fuel is much less processed in the refinery, and it will have a much lower carbon footprint in terms of manufacturing carbon footprints. And these kinds of fuels will be easily available in the future, as I pointed out right in the beginning, and it will help mitigate the demand imbalance between diesel and gasoline that is otherwise expected, and therefore improve the sustainability of refining. Another system is the octane on demand type of fuel engine system. In spark ignition engines, you don't require high octane fuel for most of the operating conditions. So in fact, it could be as high as 90% of the time. So the idea is to run spark ignition engines on low octane gasoline most of the time, and only provide high octane gasoline or high octane gasoline components when it needs it. And this has been shown to be leading up to about 5% greenhouse gas benefit. However, it will require two fuel engine systems. These kinds of systems have been thoroughly proven in the laboratory and also been shown to be working in demonstration vehicles. However, to bring it to the market, all stakeholders need to work together. And it will, of course, become commercially very attractive when the price of low octane gasoline really drops compared to the conventional fuels. So let me sum. In summary, the challenge is enormous. As I pointed out, even to replace just the light-duty vehicles in the world by BEVs will require the BEV numbers to increase by anything between 300 times and 500 times the current number. And this will produce enormous environmental, economic, and other challenges, and will be almost impossible to implement in many countries. Even then, it will only address 45% of the problem, because 55% of transport energy is still used by other forms of transport which are not light-duty vehicles. And therefore, internal combustion engines will be there for many, many decades in very large numbers. And they need to be improved significantly. And therefore, there will be significant opportunities for R&D in this area in the future. In fact, all technologies, including battery electric vehicles, are needed to address the challenges posed by the transport sector. No single technology like BEV can address these problems. Now, unfortunately, many countries like the UK are, in my opinion, very foolishly proposing banning the sale of ICE vehicles, including HEVs and PHEVs, from around 2030. All this will do is to ensure that customers in these countries will not have access to any improvements in ICE technology after this ban, even though a very large majority of transport will still be running on ICE engines. And more importantly, or equally importantly from my point of view, the ban will ensure that well before the ban comes into place, R&D in this area will stop in these countries, and a lot of talented engineers and scientists will lose their jobs. And in fact, if enough people are not encouraged or persuaded to buy BEVs by the time of the ban, the auto industry in these countries will simply collapse. And therefore, I hope many other countries which want to promote BEVs and other new technologies like hydrogen fuel cells, etc., even if they want to promote these new technologies, do not go down this foolish path and actually ban the sale of ICEs. Well, in any case now, I will simply put the various bullet points which I would like you to remember, and I've talked about it through the talk just here, and leave them here, and then we can have some questions. Thank you.